Hello everyone, and welcome back to another video. Today we're going to be integrating the Gaussian integral. So let's start. I'm first going to start off by writing it once more. And I think an important first step is to look at the integral and see if there's any way to simplify it. And unfortunately, this integral is impossible to do using standard integration techniques, such as U substitution, integration by parts, trig substitution, whatnot. If you can see, if we try right here, u equal to negative x squared, if we do du, we get minus 2x dx, and obviously there's no x dx that can appear in this integral, so it's not going to work. So here is the trick that we're going to do. We're going to label this integral I, and we're actually going to look at I squared. So I squared is just this integral times itself. So if we write this big, that's 1, and the other one, a trick here we can do is we can actually write this in terms of y. Since this is just going to integrate to a number, we don't have to necessarily write it in terms of x, so we can also write it in terms of y. And we'll see why that's important later. So this is simply I squared. Now if we look, this in terms of y, in the end is just going to be some number I. So we can just move this inside the integrand of x. So here we'll get negative infinity to infinity. I'll write the integral here. And here we'll have e to the minus x squared dx. And now, if we look, we see that e to the minus x squared has no y values inside it. It's not in terms of y, it's in terms of x. So it's really just a constant as we're integrating dy. So we can actually move this inside this integral right here. So that'll actually give us a double integral of the function e to the minus y squared, e to the minus x squared, and then dy dx. And since these are both exponents, we can actually combine them into one term. Here we'll have e on the bottom, and we'll simply add these two numbers together. Dy dx. And then I'm going to simplify this just a little bit one more time. And I'm actually going to write this integral. As we can see, if I draw this out really quick, this is the xy plane. Here we have x, y. We're actually, oh, you can't see it, sorry. We're actually going to be integrating as x goes to negative infinity to infinity, and also as y goes to negative infinity to infinity. So we're going to be integrating over the entire xy plane. So I'll just write here R2, so we know. And here we're going to have e to the minus I can pull out the negative from both of these, and I'll just rearrange it. X squared plus y squared. dy dx. But this can also be dA. And here is the crucial step. Why we did this in the first place. If we take a look here, we have x squared plus y squared. What can we do with that? Well, if you remember the last video, we proved the Pythagorean theorem. And x squared plus y squared, if we have x here, let me write this in a different color. Let's say we have a point. Well, its x is this. That's its x value, x coordinate, and here's its y coordinate. And these actually form a right triangle. So we can actually switch to polar coordinates. That's the idea that I'm getting at here. We have x squared plus y squared. We'll call this r. And from that, this distance will define r squared as x squared plus y squared. And of course, we'll also have an angle theta. And to swap to polar coordinates fully, we're also going to have to swap this dy dx. And we're going to use the formula, which I'll probably derive in another video. But the formula from going to Cartesian to polar coordinates in a double integral is dy dx is equal to r dr d theta. From now, we can substitute this all back in. But quickly, I just want to point out what this R2 is. Since we're going to be integrating over the entire xy plane, we're going to have to represent that in terms of polar coordinates also. And the easiest way to see that is for x and y, as we increase y, we go up and down, increase and decrease x, we go left and right. And using that, we'll cover the entire xy plane. But in polar coordinates, since it's slightly different, the way it's going to be is, if we increase r, we'll go up and down from the origin. So r really stops at 0, but that can go all the way to infinity. And for theta, we'll spin this little point around the origin. So we'll increase and decrease theta to spin it around. But to cover the entire plane, we only need to go from theta equals 0 to 2 pi. So that's a full circle. So in polar coordinates, R2 can be represented as saying R ranges from 0 to infinity, and theta ranges from 0 to 2 pi. And we'll put this in the integral. So now if we continue, we have I squared equals the double integral of e to the minus, here x squared plus y squared is r squared, so we have r squared. Dy dx is r dr d theta. And then since r is being integrated first, we'll put this here. R goes from 0 to infinity, theta goes from 0 to 2 pi. And that is an equivalent statement to what we said up here. And now if we can see, there's an extra r here. So if you remember from the earlier steps, we needed this x dx if we wanted to do a u substitution. But now we do have this x, but here it's an r. So we actually can do a u substitution. So let's do that. U equals r squared. I'll keep it r squared here, so we don't have to bother with changing this infinity to a negative infinity. Then we have du equals 2r dr. And from that we can see that r dr equals 1/2 du. Let's finish this integral off. Here we have I squared is equal to the integral from 0 to 2 pi. Here, as r goes to 0, u goes to 0. So we have 0. As r goes to infinity, u also goes to infinity. So the bounds are actually the same. Here we have e to the minus u. R d theta becomes 1/2 du. So here we'll have 1/2 du. And then d theta. We can pull this 1/2 outside. This will be 1/2 the integral 0 to 2 pi. And now we'll integrate e to the minus u du. Integrating that, it's just a simple inverse chain rule. We'll have e to the minus u times the negative sign. So I'll put this like this. And then that's it. And the bounds go from infinity to 0. D theta. So e to the minus u, in terms of theta, is just a constant. We can pull this out. We can pull this out here. So really we just have two statements now. We have 1/2. Oh, and this should be a limit. So limit as b approaches infinity. I'll pull the negative outside here, this negative here. Here we have e to the minus u. We have b to 0. And then we have times the integral 0 to 2 pi d theta. And we're almost done. The limit of e to the minus u as b approaches infinity, well, that's just going to be 1. So we can plug that in. We'll get I squared is equal to negative 1/2. Here we'll get, sorry, that should be 0. As b approaches infinity, e to the minus b, that approaches 0. Minus e to the 0, that's just 1. And then this integral right here just gives 2 pi. So all in all, we'll get these minuses cancel out. This is just a 1. We'll just get pi. But remember, this is I squared equals pi. We want to find I. So as a final step, we get I, which is equal to the integral of negative infinity to infinity e to the minus x squared dx is equal to the square root of pi. And of course, this is going to be the positive square root, not the negative, because this function is always positive.